Okay, this is lecture one for Water Resources Engineering. I'll cover any course information and guidelines and class lab syllabus during the class. Our major elements that we're going to cover in this course include water distribution, hydraulic processes, which include open channel flow. In the water distribution, there will be pipe flow that you are expected to know as you come into the course, but we're also going to talk a great deal about pumps and pump design. And then we're going to talk about hydrology, and this is combined in these two bullets here, where we'll talk about principles of hydrology and then the application of those principles. So as I talk during this lecture one, we're going to give you an introduction to water resource engineering, about what it is and what our focus themes are for this semester. And then I will briefly touch on some things with water in general across the United States and the world. So why do we want to study water? Water is a strong influence on society as a whole. This is a quote out of Steve Solomon's book, Water, the Epic Struggle for Wealth, Power, and Civilization. And water touches so many things and is essential for life itself. And the prosperity of a country is largely influenced by water in so many ways. Ancient Rome is a perfect example of how it harnessed water, moved water from one location to the other, clean, fresh water. The aqueducts that were designed by the Romans still stand today. And so water has a tremendous influence on prosperity in a particular country. If you look at this graph from the World Economic Forum, water touches so much of our everyday world, be it our conflict and security, to agriculture, to energy, and human and environmental health. This is an example cartoon here of well, this is an actual photo of an existing aqueduct. I would encourage you to look at this YouTube video. It's a fun video where they actually talk about Roman aqueducts and they display how a siphon works. So why do we want to study it? You know, America's historical rise, really, especially in the West, revolves around water. And even in the East, where prior to good roads, that was our main conveyance, were canals and rivers to be able to convey traffic, people, goods, products. And so we still have that in some regards on the Missouri, Mississippi, Ohio rivers, the Tennessee Tombigbee waterway. There's a lot of commerce that gets transported by water systems. If you look at water supply and distribution, this is Hoover Dam, built in the Depression era. And this dam dams up the Colorado River, and it's used for water supply. Arid parts of the western United States depend on these large federal dams to supply water, electricity, and without them, that we wouldn't have the West wouldn't be settled with any kind of population. If we look at water distribution systems, everything from the storage of water once it gets from something like Hoover Dam to a particular town. This is an elevated storage tower in Collinsville, Illinois. I think it's still there today. These are large piping systems to move water around. And you can see this through this cartoon. You know, we have to get water from its source to where we can distribute it throughout where it's needed in a particular town or municipality or business area. This is a famous quote from Mark Twain: "Whiskey's for drinking and water's for fighting." So do you really think we could have a war over water? Let's consider a few things. If you, once again, this is a quote from Steve Solomon, but if you look at where a lot of the lack of water is, it's in a very combustible, turbulent area already, which is the Middle East, northern part of Africa. Also areas of China and India, which are fast growing industrial giants, have problems with sustainable water supplies. And so those are things where when you don't have the right commodities, either for your health and sanitation or for your prosperity of your country, that can tempt people into doing desperate things and getting into conflict. So, as I mentioned, water is always very vital in arid nations, and as you see here, this is the Nile River, and they've been monitoring the Nile. It's been very important for their survival over the eons of time, and some of the oldest records we have for stream information, where they've recorded it on some regular basis, daily, hourly, or whatever, are these Nilometers along the Nile River. And you can see they got this central pole here that is kind of common to some of these, where they would record the elevations, and they mark it down and write it into their records. And we have these for thousands of years. Some of the oldest records on Earth are along the Nile River. Well, you know what? Not only do we have to worry about water in a scarcity of water, but we also have to worry about it during flooding. Water is a hazard. This photo here is from the 1937 flood on the Ohio River, which was a major flood. Was quite responsible for policy changes in the federal government. The 93 flood was the flood of record on the lower Missouri River, say downstream of Kansas City through St. Louis, and the middle Mississippi River, particularly from just upstream of St. Louis through down to Thebes, Illinois, or Chester, Illinois, that part of the reach of the Mississippi River. Here's a shot from Nashville in 2010. The Cumberland River through there flooded much of downtown Nashville, the Grand Ole Opry, some of the historic places. So water flooding is a big issue. The 1927 flood was one of the largest on record up until the 2011 flood. It was the largest record flood on the lower Mississippi River. The 2011 flood is equivalent in some respects to it, but it didn't. The 2011 didn't near the damage. It had huge impact. 1 million people were displaced, and their homes were inundated. It had great political consequences. Herbert Hoover was the Secretary of Commerce and led the United States government effort to coalesce the NGOs, non-governmental organizations, into providing relief. Prior to that, the government, federal government, had never been involved in any kind of disaster relief, and Hoover was such a household name because of his efforts during this time that he won the presidency in 1928. Probably more important was that the displacement of hundreds of thousands of Black families meant that they moved into the northern cities, Chicago, St. Louis, Pittsburgh, Detroit. Those areas saw a mass influx of people that were escaping the inundation. A lot of them were farmers, and you got to think of this: the Mississippi River was 100 miles wide in some areas, and so these agricultural lands that were flooded, people's homes were lost, and they moved north. These are photos of some flooding. Excuse me, sorry. In the 1927 flood, this is a picture on the levee system in Tennessee. Cars are being washed out. You got to remember that the only dry spot for hundreds of miles would be the top of the levee, and so people erected tents and lived there. This is Greenville, Mississippi, picture of the downtown area. And then you can see livestock in some of the dry areas. It was a devastating flood. I want to mention, I don't think I did, I highly recommend you reading this book, Rising Tide by John Barry. It's an excellent read. Not only does it describe the 1927 flood and all the different goings on at that time, but it also talks about the Mississippi River and the battles over engineering of the river by the Corps of Engineers versus other private engineers. It's a fascinating read. It's really well written. I encourage you to get it and read it. When we think about flooding, we think about water control. We try to lower our risk of flooding, lower the consequences of flooding. We do that through what's called water control. And this is a flood reservoir that's Lake Wappapello down in southeast Missouri. And you can see here, there's a large dam here. It impounds the water, and basically what they're trying to do is they hold that water back during times of high amounts of rain when the Mississippi River is flooding. They hold it back and then they release it more slowly when the river goes down. This is a picture in the lower right of the Morganza floodway, and it basically is designed to shunt water off of the Mississippi River. If you think of the Mississippi River flows to the Gulf of Mexico, and the Baton Rouge, Louisiana is here. New Orleans is right here at the mouth of the Gulf. The Atchafalaya River is a system that goes out into the Gulf, and it's a system that basically the Morganza floodway is designed to shunt water off directly from the Mississippi River down the Atchafalaya River, and that relieves this water that goes down the lower Mississippi River. So it basically provides a relief valve, if you will, and can divert water out of the Mississippi River so not so much has to flow by Baton Rouge and New Orleans. There's also another floodway, which is the Bonnie Carey, that diverts water this way into Lake Pontchartrain and out into Mississippi Sound. So this also provides a relief valve, and not so much water has to go by the city of New Orleans. So these are floodways. These are ways that we try to control the flooding. If we think about the big picture for water resources, we have water supply management, we have water excess management, and we have water quality management. Now in this course, we're not going to talk about water quality management. There are other courses to do that. In the process of worrying about these two things, water supply management, water excess management, we use two different engineering concepts that are disciplines: hydrology and hydraulics, to do this. And hydrology will be covered, as I mentioned, toward the latter part of the class. Hydraulics, well, we cover that not only in the pipe flow part of water distribution, but also the open channel hydraulics part that we're going to be covering as well. So let's tie some of the elements of the class together and look at how they fit. So I'm going to give you a couple examples here of how we might use our information we're going to learn in water resources engineering. Let's say that you had a water supply project. You were trying to do an analysis or maybe design a system that would have long-term water supply, guaranteed water supply for a particular municipality. And so you'd have to understand something about the hydrology. Let's say that the city of Rolla, we get our drinking water from the ground, but a lot of places don't have good quality groundwater to be able to provide them a source. And so if you've got to depend on surface water, you've got to have some sort of source for that. If you have a large river like the Mississippi River, well, you don't have to have a reservoir. You can just pump right out of that, because the Mississippi River, has a large yield, and so it's something that we would be looking at to withdraw. The city of St. Louis gets its drinking water from the Mississippi River. But if you had lived in a smaller town that was away from a large river, you'd have to think about how you would impound water, maybe build a reservoir that would hold the supply you needed, even when the climate turned dry or the weather got dry, you got into a drought period. And so you'd have to know something about the rainfall runoff process, what the rainfall statistics are, what you could expect in terms of drought periods. And so you'd have to design some reservoir that was big enough to see you through those dry periods. And that's the study, use the concepts of hydrology to do that. Well, let's say that you had that reservoir constructed and it was miles away from your location. You might build a canal or use a local creek to convey that water from the reservoir down to where you could utilize it at your town. So you'd have to understand open channel hydraulics, how we would convey that water. And then once we got it down there, we might pump it might build a little low head dam to capture that water, retain it for a bit in order for us to pump it and into our water distribution system. So we have to design pumps, we have to have pipes, we have to have water treatment, etc. I'm not going to address water quality treatment kind of issues. There are other classes for that, but as I mentioned, this is what we would have these three areas that we would study or we have to understand to be able to do our water supply project. Let's say that you had a subdivision. You were contracted by a developer and you were asked to do the engineering work to design the subdivision, and it was near a river. Well, you'd want to know how high that river is going to get. You don't want to be building something where it might flood, so you have to have a hydrologic understanding of the flow characteristics of that river. And you would be looking at, okay, what's the 100-year flood event for this area? And that would be maybe a 500-year flood event. You have some design standard that you'd have to adhere to, and that would provide you with a flow in cubic feet per second. But that's not what you finally need, because you need to know how high that water is going to get. So you'd use open channel hydraulics to be able to do the computations necessary to translate a volumetric flow value to an elevation of water. All right, so those are a couple of examples. So let's kind of briefly go through some review things. These are things that you've known since probably grade school. The first thing is the water cycle, and you know that whatever water we have here on the earth is what's always been here and what will always, we're not getting any more, we don't have any less, but it's in various locations in terms of various forms of the cycle, various places in the cycle at any one time. And so this is this cycle, and you see these arrows around here, and you could have the water being in the form of precipitation right now. So this is sort of like a snapshot. Some of it's locked up in ice and snow. Some of it's coursing down through the rivers. A lot of it's out there in the oceans. Some of it's down in groundwater. Some of it's being evaporated or evapotranspirated. And the evapotranspiration is a combination of evaporation and transpiration, which you get from plants. Plants transpire, and so that moisture that comes off those plants, that's the transpiration part. And in hydrology, we often combine the two and call it evapotranspiration. So all of our water is in various locations in time and space, and it's constantly evolving. If you think of, there's 326 million cubic miles of total water. 2.5% of that is fresh. So fresh water would mean it's not brackish or saline. It's not, salty, where you can actually use it. And half of that is tied up in ice and snow. And so 0.75% of that is tied up in the groundwater system, or is in the groundwater. And the rest of it's in fresh surface water, like rivers and lakes. So you kind of get an idea of perspective of where all this water is. Now this graph here, or this figure here, kind of gives you an idea from just a percentage. If this is the total amount of water available in the water cycle, what's here on in this globe, you can see that the majority of it's salt water. And then, as I said, you get 2.5% is fresh water. Most of that is in the glaciers and permanent snow cover. And then you've got a lot in groundwater, and then you've got some in the lakes and rivers. So you can kind of see that there's not a lot available for us to be able to utilize for the various purposes that we would utilize it for: drinking water, manufacturing, agricultural, or what have you. So this is another shot of the water cycle. You can kind of see quantified. You get some numbers here, and this is in metric units of where it would be at any one particular time. So let's think about what's something called recharge. Recharge is kind of, think of it as turnover. How long does it take to, if you draw water out of the ground, how long does it take to replace that water that you drew out? And for groundwater, that's days to millennia, whereas in surface water, basically on average is about 16 days. And so in the groundwater system, if we've got karst, well, that's high. That's very fast, rapid recharge, because karst is where you have solution cavities, caverns. I mean, think of it as in limestone or dolomite, where you've got a lot of calcium carbonate, and that depending on the pH of the rainwater, can dissolve over time. And so you get these solution cavities and you get a really rapid inflow from the surface down into the groundwater system. This is a problem whenever you have some sort of spill on the surface. It can rapidly get into your groundwater system and be a problem for you. Areas like Springfield, Missouri, they have a karst area for their recharge in the groundwater. So it's very easy to contaminate the groundwater source down there. Now, areas that are, say, northern central Illinois, which has got a lot of basically glacial deposits from the days of glaciation, and you have this this really deep layer of clay, silt, where it's fairly tight. It takes years, thousands of years in some cases, to recharge those aquifers. So you get an idea of how fast things can turn over in a groundwater system. Whereas in surface water, you know, it's fairly quick. You know, from the time water precipitates on a landscape somewhere to the time it goes out into the ocean, it discharges to the ocean, the sea, is a matter of days, and then on average 16 days, according to a particular reference here. And so if you look at this, this is sort of another shot of periods of renewal. I used to, on the previous slide, we called it recharge. You can see here's our channel network, 16 days. You can look at the ocean, total turnover, renewal of the ocean, 2,500 years. So you can kind of get an idea of how things vary with the source. If we look at our water reserves, I'm not going to go through these numbers, but you know, we look at our total water as a percentage of the global reserves. So, you know, basically fresh water is only 0.76% of the total amount of water that's available out there. If we look at of fresh water in the groundwater system, you're 30.1%, whereas we look at water reservoir reserves in lakes and rivers, we're talking about much smaller amounts of the fresh water. Again, it's just another way to present what I've already talked to you about. So where is the world's fresh water? And this graph is this map is a very interesting map. When I was talking about wars over water and where we have the shortages, you can see this this key the key here is the warmer colors. This orange says that between 0 and 1,000 cubic meters per person per year are available in those areas. So that's not a lot of water, whereas the dark blue, that's water-rich areas. You can see that's, you know, between 50,000 and 605,000 cubic meters per person per year. And these are areas that are water-rich, and you can see where they lie. They're very dark blue. And so where you've got a lack or a scarcity of water is in this area here. You can see India. Here's the Middle East. This is the northern part of Africa. And those are areas which you know, you have big problems with getting and guaranteeing a good fresh supply of water. Again, if we look at this, this is from the water availability standpoint, world water availability. Again, this is just showing those numbers. Here's the United States. Here is northern part of Africa. Here's the western part of Asia. And I don't see, I thought I'd see the Middle East here. I'm not seeing it, but you get the picture. So how is it used? How is the water? So you can see, and I'm going to show you a second from the USGS where they look at the water use in the United States, but this is just on the world scale of things. And so we've got various types of use. So there's agriculture, there's industry, municipal supply, reservoirs. You can see that at least on the world standpoint, we use most of our water in the agricultural process. And we use the next highest user is industrial work. And so, you know, you can see that we're, you know, agriculture, you know, we're growing things. We're you know, that's for our food consumption, either crops or livestock. So as I mentioned, you can go, this is the USGS water use report for 2010. These are done basically on about an every 5-year basis. And in this, the USGS characterizes the uses of water by these main categories: public supply, domestic, irrigation. You can see agriculture gets broken into 3 different components here. and not just lumped into one big one. But then you've got industrial, mining, and thermal electric. And so if you look at the total withdrawals in the United States, you can see the big users of water. Texas, California are the two biggest users, at least for this. I think this is the 2005 report, this graphic here is. But you can look at what we're looking at is we use 354 billion gallons per day in the United States. But that's in 2010. That was down from what we used in 2005. And the big user, thermal electric and irrigation. And you can see that, thermal electric, 161 billion gallons per day. Now, you can see population here in pink. And you can see water use by type, total, surface water, and groundwater in blue. And you can see that it's kind of leveled off. And a lot of this corresponds to the fact that the large cities used to not meter the water going into your home. And so you could, if you used it, 25,000 cubic meters of water, or you used 100 cubic meters of water, you're going to pay the same bill as either way. Now the large cities, now they meter their water. And so now you have a water meter, so you pay by your usage. And guess what? When you have to pay for it, the use goes down. All right, that concludes lecture 1.